Hello and welcome back. In this session we'll cover algebraic structures such as groups, rings and fields. Very important topic that will combine a lot of the concepts that we've talked about so far and also form the foundation for a lot of mathematics. So please join me for groups, rings and fields in this session on algebraic structures. So let's define what an algebraic structure is. These are also called mathematical structures. So first, in order to do that, let's consider an n-ary operation on the set X. N-ary means it takes n arguments, where n is a finite number in the set of natural numbers. So we have one or more operations defined on the set X, and we have the set X itself. Now, an algebraic structure is the combination of the set X along with one or more n-ary operations on that set. And the only requirement on the operation is by the definition of the operation itself, is that it's closed on all elements of the set. We use this tuple notation to denote mathematical structures. So these are parentheses brackets, and then we list the set along with the operations that take part of the structure. An example is the set of natural numbers with the binary addition operation. That's an example algebraic structure. Now we're going to go from simpler to more complicated algebraic structures, and we'll start with a structure called a magma. A magma consists of a set X along with a single binary operation on that set X. So consider the binary operation O plus on X that takes two inputs on X and maps back a single output on X. And one of our simplest possible structures, a magma, is the set X along with that binary operation O plus. And the only requirement is that O plus is closed by the definition of operation on all elements of the set X. Some example magmas are the set of natural numbers with the addition operation, as well as the Boolean domain, the set of Boolean numbers with the OR operation, Boolean addition. There are other examples, but these are two that we'll start with. Now let's move on to a structure called a semigroup. A semigroup is an associative magma. So it's a magma with the additional requirement that its binary operation has the associative property. So consider again an arbitrary binary operation O plus that maps order pairs in the Cartesian product of X with itself back to single elements in X. The only requirement here is that that binary operation is associative. Besides the fact that it needs to be closed, which we inherited from the magma. So semigroup is an associative magma. And remember, the operation is a binary operation, it's arbitrary, so it can be multiplication, it can be addition. We've used the symbol O plus to denote an arbitrary binary operation. Now, we again have the examples that we had in our magma, the set of natural numbers with the addition operation, or the set of Boolean numbers with Boolean addition, or the OR operation. Those were example magmas, but they are also semigroups because both those operations are associative. Our next structure is called a monoid. And a semigroup is a monoid if it has the identity element for its operation. Now, remember, an identity element U is an element in the set X such that for our operation that we had O plus, X O plus U equals X for all elements in X. So again, a semigroup is a monoid if it has that identity element, and that brings the total list of requirements for a monoid to be the following. So first is closure that we inherited from the magma. Second, we must have the associative property on our binary operation O plus. And third, the binary operation O plus must have the identity element. Examples are again the set of natural numbers and addition, as well as the Boolean domain and the OR operation, or Boolean addition, because both of those we discovered had additive identity elements, as we have discussed previously. So both of those are monoids. Our next structure is called a group. And a group is a term you've probably heard before, since it's commonly discussed in math. Now, a monoid is a group if it has an inverse element under its operation for each element in the set. So the requirements for an algebraic structure to be a group are the following. First, we need closure, which was inherited from the magma. The operation must have the associative property. Now, the operation must also have identity element u, such that for all elements x in the set x, xo plus u equals x. But we now have a fourth requirement to make this a group, and that's inverse elements. So we must have elements xi for all elements x, such that xio plus x equals u. So here we're showing the left inverse. Typically we have a left and a right inverse, so that xo plus xi equals our identity element u as well, and this is for all elements in x. This means that the structures we gave as examples, such as the natural numbers and addition, and the Boolean numbers and the OR operation, are not groups, and that is because they do not have inverse elements for all elements in the set. The natural numbers don't have inverses because we don't have the negative numbers. So under addition, there are only inverses for a single number. The same is true for the Boolean domain. So the Boolean domain and the OR operation, natural numbers and addition. So Boolean and addition on natural numbers, there are no additive inverses for all elements. These are not groups. We do have an example here that is a group, and that is a set of whole numbers under addition. And that's because the whole numbers do include negative numbers, we have additive inverses. So the set of whole numbers with the addition operation is in fact a group. Our next structure is called an abelian group. It's also called commutative group, and the word commutative says it all. A group is an abelian group if its binary operation is commutative. So an abelian group has the following requirements. First, closure, inherited from the magma properties. Then its operation O plus must be associative, which is inherited from the semigroup. We must have the identity element, which is inherited from the monoid requirement. Then we must have inverse elements, which were required by the group properties. And now we have that the operation must be commutative. That means that xo plus y must equals yo plus x for all elements xy in x. We do also have a structure called a commutative monoid that has all the above except inverse elements. So we can also have a monoid that's commutative. We'll call it a commutative monoid. The structures of natural numbers with the addition operation, or the Boolean domain with Boolean addition, or the OR operation, those are commutative monoids because we saw they didn't have the inverse elements for all elements in the set. So far we have been describing algebraic structures that consisted of a set X along with a single operation defined on that set X. Now let's consider two arbitrary binary operations defined on X. The operation O plus and the operation O times. We can now describe a ring is an abelian group with a second binary operation that's at least a semigroup, and the second operation distributes over the first operation. So structure x O plus O times is a ring if xo plus is an abelian group and x O times is at least a semigroup, and O times distributes over O plus. And for some examples we can actually substitute O plus for addition, just plus, and O times for multiplication, just times. And we'll see that both the whole numbers along with addition and multiplication, as well as the real numbers along with addition and multiplication, are rings. The second group here, the multiplication operation, does not have inverse elements for all elements, but it is at least a semigroup. In fact, they are monoids in these cases. So both of these structures are rings. Now, the last structure that we'll discuss in this session is called a field. A field is a ring where the second operation is an abelian group on the set X if we exclude the zero element. So if we again consider arbitrary binary operations O plus and O times, structure X O plus O times is a field if X O plus is an abelian group and X minus the zero element O times is also an abelian group, and O times distributes over O plus. So the difference with a ring is that the second operation is an abelian group on all elements of the set except for the zero element, if we exclude the zero element. So we defined the set difference before, so it's an abelian group on X minus the zero element, denoted with this backslash notation here. Now, examples of fields are the rational numbers and the real numbers under addition and multiplication. And that's because we have additive inverses for all elements in each of the sets, and we have multiplicative inverses for all elements except the zero element. So in both rationals and reals, multiplicative inverses are 1 over x, and those exist for each element except for the zero element. And that means that the rationals and reals are fields under addition and multiplication. Let's summarize this session. We defined algebraic structures as sets with one or more operations defined on that set. And we went from magmas to abelian groups by adding requirements, axiomatic requirements, things like associativity, commutativity, identity elements, etc. So we can think of these structures as a set of magmas where semigroups are a subset of magmas that are associative, and monoids are a subset of semigroups that have identity elements, and groups are a subset of monoids that have inverse elements, and abelian groups are commutative groups, so they are a subset of groups. And we can think of rings as a subset of abelian groups that have an additional operation defined on them, where the first operation is abelian and the second operation is at least a semigroup. And fields are rings where the second operation is a group if we exclude the zero element.